Here we're being asked to compute the integral of secant of x. Now, the strategy we're going to use is neither obvious nor intuitive, but what we're going to do is let's rewrite our integral, so integral secant of x, and we're going to multiply both the numerator and denominator by secant of x plus tangent of x. Now, why would we want to do this? Well, we're going to notice in a second, but let's go ahead and just multiply this out. So in the numerator, if we distribute, we'll get secant squared of x. Secant times the tangent, we'll get secant tangent. And in the denominator, we'll just maintain the secant x plus tangent of x. Okay, so looking at this integral, we should notice that the derivative of secant is secant tangent. So the derivative of this term is right here in the numerator. And we also should see that the derivative of tangent is secant squared, which is also in the numerator. Therefore, the derivative of my denominator, secant x plus tangent x, is equal to all of the terms in the numerator if we were just to flip these, right? So secant goes to secant tangent and tan goes to secant squared. So our denominator, its derivative is actually in the numerator. This tells me this would be a good integral to use a u substitution with, right? When we do u sub, we're looking for a term whose derivative is also in the problem to choose for u. So we're going to go over here, and what I'll do is I'll say u equals secant x plus tan x. Therefore, du is, again, secant goes to secant tangent, and tan goes to secant squared. If it helps here, we can put our secant squared term first. And therefore, our integral becomes the integral of du over u. We should know this as the natural log memorization rule, so we end up with natural log absolute value of u plus c. Then we just wrap up by plugging back in for u. We see that we get integral of secant x dx is equal to the natural log absolute value, secant x plus tan x, plus a constant c because we do have an indefinite integral. That is our final answer.